Thank you to Marianne and Scott. So today we're going to go ahead and be talking about how we can make your SQL Server queries go faster. As to Marianne mentioned, my name is John Starrett. I'm highly involved in the SQL Server community. If anyone attends any of the virtual chapters, I'm highly involved in those and even run the High Availability Disaster Recovery virtual chapter and a local SQL Server user group here in Austin. My main areas of focus and also my passion is with performance tuning. So a lot of the code samples we're going to be going through here today are a bunch of lessons learned that I also see repeated over and over and over again out in the field. So, root cause analysis for SQL Server. One of the biggest mistakes I see all IT professionals do, whether they're in real live production DBA, a developer, or even just an IT professional, is they don't know how to do a really good root cause analysis to find which statements they should really be focusing on. A lot of times people end up focusing on queries because someone comes to them and they say this query is slow. You really have no idea if it's the actual query that's the root cause of your problem or it's just a symptom of a bigger problem out there. So we actually have a video that's recorded that's out there on Embarcadero's community website, which I really suggest you go look at, which will show you step by step how anyone who's watching this webinar can start capturing workloads so they can find their top offenders. Also, performance tuning can be a lot like whack-a-mole. You have one pop-up that's a real pain and you end up solving it just to find out that you have a lot of other pain points popping up. That's where the root cause analysis can be very helpful. Once you have that, it's also good to have a good checklist of patterns, of anti-patterns, that could be very friendly for people writing the code, but not so friendly for the optimizer itself. So here's our agenda here for the next hour. We're going to go ahead and show you quickly how you can identify bottlenecks by using extended events, which is built into SQL Server Management Studio. I'm also going to show you how I go about benchmarking queries, so you have a good before and after case, so that way you know exactly how better or worse your query is based on your changes. Then we'll take a look at some execution plans and go over some of the good, bad, and ugly stuff I see repeated over and over again with indexes. And we'll spend most of our time looking at T-SQL anti-patterns. So from this point out, we're going to go over to Management Studio and we're going to go through these demos here. So hopefully you can get some good insight into ways how you can modify your code to make it more friendly and run faster on your SQL Server database. So the very first thing we're going to do is we're going to take a quick look over at extended events. So by default, inside of Management Studio, under Management, you will see extended events, and if you have any sessions, they'll be down here. Quickly, I'm going to go ahead and show you how you can create an extended event that will allow you to capture your top offenders. So the very first thing you're going to see is when you right-click, you can actually go and say, let's do a new session by the wizard. I'm strongly going to recommend instead you actually create a new session because you're going to see this is a wizard and it's actually going to give you a lot more flexibility into what you can do. So to start off, we're going to go ahead and give it a session name here. Call it Embarcadero here. Now we can select the events that we want to capture. And let's just say there's so many in here we don't know what we want to look at. Well, if you have a statement that's running, at some point it's going to have to complete. So as soon as we type in complete, you're going to see this is already going to filter down to everything of your events that only have complete inside of it. So we can go ahead and select statement completed. And just in case you don't know what this is, you're going to get your description here, which this will tell us all of our statements that's running inside of objects like stored procedures will be caught here. And even here is all of the events that you can use to catch. So we're going to go ahead and we're going to select this, and we're going to get our SQL batch over here. And now we're going to go over and configure it. So you can see here we have both of these highlighted. So as we make changes over here, it'll affect both of our events that are selected here. So there's one action that we want to make sure we always add, and that's going to be our query hash here. So I'm going to go ahead and zoom back in, Because every time you run a statement, whether it's select star from big table or any other statement, you're going to get a unique hash that you can then aggregate on. So that way you can figure out the whole total duration or the average duration. Same thing for reads or writes. So in this case, we won't even have a filter for today's demo. Now we're going to look at how do we want to store these events that occurred. So you're going to have a couple different options here. Two are pretty much used mostly with extended events. The first one's ring buffer, which is just going to put this into memory. So as soon as we lose our instance or we restart our instance, we're going to lose everything here. The next one, if we want to persist these events, would be to store it to a file. So for today, we're going to go ahead and we're going to look at a ring buffer. And we're just going to go with the default properties in here and let this run. So now if we kicked off a workload here, we would go ahead, we could start this and it would capture everything live. Today for our demo, since we only have an hour, I have a pre-captured trace here, which we're going to go through and take a look at and show you why extended events could be very helpful for you. So here's exactly what you would see inside a profiler, but this is where extended events is going to be extremely helpful for you. We can now do grouping, and remember I said you want to make sure you had your query hash here because now we can aggregate on it. So instantly we went from a whole bunch of statements to finding out we really have 3 statements that ran 500 times. So we can instantly slice that down so we can aggregate our metrics based off of what was ran. So now we're going to go ahead and we're going to add some aggregations so we can find our pain points. So for example, if we want to look at the sum of our duration, the sum of our writes, and we'll go ahead and take the sum of our reads. So that would be the total amount of reads, total time, and the total amount of writes. Now we can go ahead and say we really want to focus on the statement that took the most total time. That's where we can go through here and do our aggregation by duration and tell extended event we want this in this order. So by doing that, it instantly go ahead and sorted all of our statements so we could see which one took the most time and grouped everything together. So for anyone out there that has never had a process of going through and finding your top offenders, this is an easy process that anyone can do because it doesn't involve you writing any code at all. In fact, we even got a real nice video on Embarcadero's community website that you can go to and see this in detail if you want more step-by-step breakdown on how you can capture your top offenders. So now that we know how to capture our top offenders, let's go ahead and dive into some of our examples here. So first we're going to go over how I go about benchmarking queries. So the very first thing I'm going to do is I'm going to jump into our database here. And I'm going to use set statistics. And I'm going to use this for 2 different reasons. One, I want to benchmark and know exactly how much I/O is going on. So how many pages are we reading or writing as we're baselining our statements? The next thing I want to focus on is time. So how much CPU time? Are we going parallel and we have more CPU time than duration or vice versa? The next thing, and this is something I strongly suggest you do when you're able to benchmark in a non-production environment, is I want to clean out all of my memory. So this way I have my starting point that will always be consistent no matter what I'm doing. So there's a couple statements in here I'm running, and I'm running them in a particular order for a reason. The very first thing I'm going to want to do to set up my cold starting point where I have nothing in memory is run a checkpoint. Because what a checkpoint's going to do is it's going to go ahead and take all of your data that's changed in memory and flush it out to the data files. The reason why we want to do this is because we can only drop clean buffers. There is no way for us to drop dirty buffers. So the checkpoint up here is going to make them clean so that way they can be flushed out. Finally, over here, we're going to go ahead and free all of our plans that are in memory. So we're going to build new plans. If you wanted to, you could pass in just a handle for the plan, but for today's demo, we're just going to go ahead and free them all since this is not a production environment. So we're going to go ahead and turn on our set statistics I/O time here. And then we're going to run our very first statement here. So very similar. We're going to have a select star from a table called persons, and we're going to select 3 columns, first name, last name, and middle name here. So most people will always assume that this second one will run faster, mainly because we have select star up here where we're only selecting specific columns. The real answer to this is it depends, and this is how I'm going to show you how I go about baselining queries. Because when I run this and I turn on here, I want to look at my actual execution plans. We're going to see some interesting data behind our queries that are running. So the first one's going to go ahead and select every column, and the last one's going to select just the 3 columns we need. So if you've never looked at an execution plan before, there's a couple things I want to point out to make this easy for you to get started with. Every query will get assigned a cost, and here we can see that we have 50% cost for both select star in here and our select with our 3 columns in here. Also, we're doing what's known as a clustered index scan in both. So the actual data that we're going to return here and go through to pull our data is the same, and we'll see this when we look at our set statistics IO. This is where indexing is going to come in to help you out. So if I look at our set statistics here, this is where we can take a good look at what was actually pulled. So the very first thing you want to look and make sure is that your rows affected are the same, which we see here. The next thing is, because we're using our clustered index, which is how the data is physically stored, we're seeing our logical reads here are exactly the same. And the nice thing, because we don't have a lot of index fragmentation, even though we're taking advantage of read ahead, we're only doing it once. So this is how we know we have a good cold starting point that's giving us the same result. The only difference here is our elapsed time, because in our first example we're pulling back every single column, where here we're pulling back just our 3 columns. So from this you can see exactly how you can look at set statistics IO to figure out exactly how much IO you're pulling back. You can get the time, and you can also look at your execution plans at the same time to see how they're different based on your changes, which is going to help us once we start looking at indexes. So now we're going to alter this query just a little bit. I'm going to go ahead and run SB help here, so that way I can see what all is included on this table. So that way I can see what indexes currently exist. And here we're going to see our indexes that are currently in play. We don't have an index at all on any one of the 3 name columns here. So this could be a good candidate for adding an index. So now we're going to go ahead and look at the same statement, except now we're going to go ahead and add a filter. So when I run this again, we're going to see a statement that looks very similar. We're still doing our clustered index scan over here because we don't have an index that's going to help us. Now, one mistake I see repeated often out in the field is you run a plan, you look at your execution statement, and you see this really nice helpful thing called a missing index hint. So too often out in the field, I'll see people always add this, and this can end up causing performance issues when you're doing your inserts, updates, and deletes. So we're going to actually go through and do an analysis here, and we're going to go ahead and add our index here on our filter. So when we started, as you can see here, we have 3,000 logical reads. When we go ahead and we add our filter to filter down on our last name here, this is going to go ahead and cut this down for us. So we're going to go ahead and rerun our query. And we're going to see a different execution plan. Before you only saw 1 operator, and now we see 3 in here. So for all my developers out there, when you see a nested loop join, to you this is a for loop. This is the same thing as saying int I equals 0, array dot length I++. For everything inside of here, we're going to go through here and down and do everything in here. So this is your typical for loop. So this can be good, but this also could be bad, because in this example, we have our filter, last name like Smith, so we're seeking, which is great, but we have to go and pull all of our first name columns here, which is why we're going down to our key lookup over here. So looking back at I/O here, we can see that we went from 3,000 down to 300. So this is great. By adding one little index, we improved our reads by a factor of 10. But we can even make this better. So because we have select our first name and our last name here, we can do an included column. So we're not going to include first name in our filter, but it'll be tagged along for the select part of our query. So when we do this and we rerun our query, we are going to go from 300 logical reads down to 4. So you're not going to get this much better than this. And I always love seeing queries that run in 1 millisecond. It's usually hard to make those go faster. And also, when we look at our execution planning here, you're going to see that we went from 3 operators down to 1. And we have an index seek. So this is about as good as you're going to be able to make this. But this is where I see things start to go bad. What happens when you have a part of your code that calls the very same statement, except maybe more columns are added? So in this case, we're going to go ahead and add an extra column here to get our middle name. So when we run this query, because we already have our index that has the included first name, we're going to go back over to our key lookup. So once again, for loop for all my developer friends out here. Every time we're going to go ahead and do an operation here, we're going to do it for everything down here. So out in the field, what I typically see is a DBA or someone who's overlooking the indexes strategy will just go ahead and add a new index. So basically, we're going to have 2 indexes that are identical, except for the fact the second one has middle name tagged along with it. So we'll go ahead and we'll create this. So now when we rerun our query that has middle name tagged along to it, we're going to get back to our index seek over here. So while this looks good from the select portion, we now have to worry about how our data is changed through inserts, updates, and deletes, which is why I added the second query. The second query, which will be included with the link of all the source code from today's presentation, can be used to find overlapping indexes, or what is known as partial duplicate indexes. And the one thing I want to point out from our example here is we just created one. So even though we really only need our second index here, both indexes are going to be inserted, updated, and deleted. So anytime data changes, both these indexes have to be managed, even though we're never going to use this one because our second one will satisfy both queries that we were looking at. So a key thing that I want to point out here is don't just look at the execution plan and always add an index it recommends for you. You really need to do some research and look at what you currently have, because there's a very good chance that you have an index that will work if you just tweak it a little bit to add a column or 2 as included columns. So to clean this up, we could just go ahead and drop our first index. And from there, we will be good to go. If I run both statements here, we're going to see that our second index here, we can see this by seeing which object is being used inside of our execution plan. Here you can see that middle name too. Will be used for both queries. So once again, please take care of knowing what indexes you currently have before you go adding them, because this is where I see out in the field over and over again performance problems start to pop up with inserts, updates, and deletes, because new indexes are constantly being added, even though there's ones that are existing that can handle both queries if you just take a look at them and make a small change. So next we're going to hop over to another repeated pattern I see out there in the field a lot. So before I became a DBA, I was a developer myself. I did lots of development, what I would call the Microsoft potluck, which was classic ASP all the way up to C# 3.5 before I moved over to being a full-time DBA. And because of that, I loved reusable code. I was an object-oriented programmer, so I loved creating objects that I could reuse. This makes a lot of sense as a developer. Unfortunately, you'll see here that this may not make a lot of great sense from the optimizer's perspective. So here I'm going to go ahead and, oh, it's already there. Let me clean this up. We'll just go ahead and recreate in here. So I'm just creating a function that'll go ahead and take in a product ID and get me the max amount of quantity for that product. So at the same time while this is running, I'm going to go ahead and make sure that we're watching live data here. I'm going to show you why this is not a great thing from the optimizer's perspective. We're going to go ahead and get our clean starting point. So we did our checkpoint, we dropped our buffers in memory, and we freed up all of our plans. We're going to start tracking our set statistics IO in time. And so now we're going to run this query here. We're going to have our user-defined scalar function here as part of the select. So every time this runs and it has a row for product, it's going to go ahead and take it and put it inside of here and get you the output. So this is going to produce what's known as row-by-row processing. So if you remember, we have our function here that's focusing on the sales order details in large table. So when we run this, we're going to see some very misleading data back from it, our execution plan and our set statistics that are running. And another indicator to tell you that this may not be a great thing is you can see that we're still running as we've gone 10 seconds into executing this one query. So this will take a little while. And the reason why, just to show you, the reason why I turned on watching my extended event trace is because for every single row we have in here, we're calling that function row by row by row by row, and we're waiting for it to return. And here we can see it finally did. It took us 29 seconds over here to do row by row processing on 504 rows. But this is where things get really interesting, because I already showed you how I go about benchmarking my queries. And you should be wondering, by looking at this, why did this take 28 seconds, John, if we only did 4 reads? Remember, we only have our product table in here, so we don't even have any metrics by that enlarged sales order table that we use in our function, because it's going through row by row processing to read this. If we weren't looking at our live data that captured everything that was going on row by row here, we would just see that this query took forever and we have no idea it was doing row by row processing behind the scenes. So you're always going to want to try to stay away from using scalar functions when possible. So how do we fix it? There's a couple of ways on how we can make this much better. One is to use what's known as a user-defined table function. So this is going to allow us to use set-based logic instead of row-by-row logic to actually take all those product IDs and to get the max values for them. So once again, we're going to get our same starting point here by freeing out our data pages and our execution plans. And now we're going to run the same select statement that has a little bit of a modification to how it's written, but it's going to give you the exact same results back. So I'm going to do a cross apply, which basically is saying I want to take this table as one operation. And I'm going to go ahead and pass in product ID into this function. And then we see max quantity over here. That's going to be the output. And it's going to go ahead and allow you to put that over there so you can select from it. So by doing this, we're going to have one set-based access instead of row-by-row access here. So before we saw this took over 20 seconds, we're going to see this completed in 4. So just doing a real quick change of taking your scalar function and putting it into a user-defined table function, we now have our whole execution plan. So there's a couple things to point out here. The first thing is we see we have operators for both tables. The other nice thing you're going to see here is we have these 2 little arrows, which means these operators went parallel. Because it's not a scalar function and a table function, it doesn't inhibit you from being parallel and taking advantage of your CPU threads that you have. So while this looks like more work, it's just not hiding everything that's going on row by row. So we can see our logical reads here for each one of our tables. But the key thing here is by making a small change, we went from over 20 seconds down to 4 seconds. So next we're going to jump into another favorite topic of mine, which is known as sargability. So when I say sargable, what I mean is searchable. So when you have an index, a normal index, you're going to be storing your data into a B tree here. So what you want to do is be able to seek it to find the data you need instead of having to scan all the way through your data. So going back to our person example here, we have 2 similar queries. The first one up top here is called, we're going to basically search for last name that has Smith inside of it. Because the optimizer sees this % here, it's going to have no idea what it can skip. So because of this, it's going to be non-sargable because I can't seek through the index and just pull what I need. If you need to do operations like this, I would highly recommend looking into full text search or other options outside of SQL Server. Now, on the other side, when you are able to actually start without a wildcard, now we can search through. And we can actually go ahead and find all the records that have a last name that start with SMI and just pull everything after it that still matches it. So when we run these 2 side by side, we're going to see a couple of things. So let me zoom out so I don't have that tooltip hiding what I want to show everyone here. So even if you never looked at execution plans before, you can clearly see that the top one has 97%, which means 97% of the total 2 statements was spent working on this first query. Also, we have our index scan here, where down below we have our index seek. So once again, this is green. It's good because it's sargable. What I love about SQL Server and its execution plans, you can kind of see that because if you look over here, you see the arrow going and searching and just going through one path. Where up top here, you see it going through everything. So this means that it's scanning because it has to go through every single page in your index. Or down here, we're just going through what we need. So another real-world example I see repeated over and over again is a case where you may have a web page and you need to return every person that has, a last name starting with S. So out in the field, what I'm going to see way too often is a scenario like this where I'm going to apply a substring on the column we want to search against and tell it to get me the first character. And then I'm going to do this wildcard to say, hey, I want it to be S for all the S's in the alphabet there. So whether it's Smith, Starrett, it'll return it all. You can get the exact same result by just tweaking your where clause here to have last name like, and then have your % after the S there. So this gets you the exact same results. The only difference is the second one is going to be sargable for us, and the first one isn't. So next we're going to look at dates. All too often I will see many examples where The table is using either date time or date time 2, so you have your date and your time attached to it. And people want to end up filtering only on that date. So they basically are wanting to stripe off the time and only pull back all the records for a given date. So this is an example that I'll see to do this all the time. I want all the records for July 27th of 2008. In order to get this, I will see people do conversions here, and then on top of that, cast it back out. This is all going to make your index have to scan through all the pages instead of seek right to the pages it needs, because this is going to be non-sargable. So just to show you here, when we look at our execution plan, we are going to see that this is going to do index scans across. So instead of seeking and only pulling what it needs, we're going to scan across the whole entire data. So how can we do this another way? The easy best practice that I would recommend for you to do is what I'm going to show you here below. If you want all your records for the 27th of July, make sure that you have your greater than equals to this date, because this will pull your 00, your first possible time in this date. And then you're also going to want to add another filter here for the first time in the next day. This will guarantee that you get any record that falls on that date. What I see people do in the field, and they find out it returns them a result set they weren't expecting, is they'll use between. And the reason why I recommend that you don't do this is because you may not know this, because you may not have any data that matches up, but this is going to include this data point. So you will get everything that happened on the 27th plus this very first time period on the 28th. So when I go ahead and run this query, we're going to see that we get similar execution plans, but the cost is different. And the reason why is because when we actually look at the rows here, we're going to see our first one's going to get 2,600 rows. And our bottom one here, and I'll even scroll down so everyone can see that we have some data there on the 28th that start off at that first time interval. When we go ahead and scan down here, we're going to see that our row numbers don't match up. That's because we may not know that when we use between, it's actually including that last date in there. So you want to be careful about that. So next we'll look at how do we modify to where we want to change the date we're pulling. So in this case, I'll see this repeated in the field where we'll apply our date add to the actual column. When you do this, it's going to make your query non-sargable. I strongly recommend that you change your literal over here that you're going to compare to. So you always want to, when possible, to not add any functions to your columns that you're filtering here. So we'll go ahead and we'll run this. And same thing we're seeing here, that we're scanning across the top. It's 99%. So 99% of our cost bad. Seeking, and this only being 1% much better. So in our last case here, which is very interesting, I see a lot of reporting queries out there where people want to pass a parameter, and the parameter may not be used, so it may be null. And we want to return data if it's null. So I'll see a lot of times coalesce being used, because coalesce will basically look at our first parameter here. And if this sales order ID value is null, then it's going to go to the second one here, which obviously is not null, and it equals what we're passing in. So this is non-sargable. And if you've paid attention here and you've heard me say, don't add functions because it'll make your filters be non-sargable. There's a couple of edge cases to that. So when I actually run the second one, isNull is a T-SQL function. It's not an ANSI function. So because it's a T-SQL function, they've built in code in the optimizer to make this sargable for you. So just to show you here, this is sargable. We're actually seeking through it instead of scanning. And you'll see here that it even adjusts your predicate. So this is all the optimizer behind the scenes, changing the code for you to make it sargable. So if you ever have to build a report to where you may have parameters passed in that you don't want to always be used and can be null, I'd recommend that you take a look at isNull instead of using coalesce or other methods out there. So next we're going to go ahead and take a look at temp tables versus table variables. I see a lot of misleading information out there on the internet about both of these. There's a couple things I want to make sure everyone is able to see from this demo here. So same thing, we're getting our starting points here by clearing out what's in memory. The first thing I see all the time out on the internet is one of the downsides to table variables is you cannot have any indexes or a clustered index. And I'm quickly going to show you that's not true. You can specify when you create your table variable that you have a primary key that's clustered, and that'll get you a clustered index on it. So through this example, I'm just going to basically go in here and add some data. And then we're going to use that data in here to do our filtering. And we're going to go ahead and join off of our table variable that we added. And there's one thing I want to make sure everyone understands from this demo, if it's only one thing you can take from it. If you use a table variable, you need to understand that the optimizer is always going to assume you have just one single row. So if you're working with real small data sets, table variables could be a very good thing for you. If you're pumping a lot of data, you probably don't want to be using table variables because it's always going to assume you only have one single row. Now there's a little catch to this, and I hardly ever see this out in the field. But just to make everyone aware, you can add option recompile. And what this is going to do is every time this statement runs, it's going to recompile it. So then it's going to be able to look at statistics. So here we're going to see that we actually have good statistics. The big catch here is now you're telling the database engine to recompile this statement every single time it runs. So you're going to need a lot more CPU in order to do this. So with that, we'll go ahead and we'll look at a temp table works behind the scenes here. Exact same thing, we're just creating our temp table instead of a table variable. We have our same primary key clustered index here. And we're running the same statement. So the interesting thing that you'll see here is not only do we have good stats, but we also have a different join here. We're actually going to use our merge join. So same thing when we look at our stats here, we have good stats. If this was a query that needed to go parallel, it could, where our table variable wouldn't allow you to. So the key thing for you to take from this demo is if you're working with a big set of data, you're probably going to want to consider using temp tables if you need them compared to table variables. And so with that, we're going to go ahead and jump into our next demo, which is going to go over CTEs and how they can be misused. So I once worked for a pretty big enterprise consulting company that built their own reporting framework to where everything went off views. And when you have small views like this one here, that's not a bad idea. In fact, this two queries side by side will show you exactly how views really work. They're just the same as a derived table. So even though I'm doing select star from my CTE, which I'm creating in here, this gives you the exact same plan and is not different at all from doing select star from derived table in here. And when you keep them simple, this is perfectly fine. Where this starts to go south is when you have a bunch of nested CTEs on top of each other. So in this case, I have one to get my sales total. I'm doing another one to get the quota information, and you can see this here. And I'm doing a third one on top of that to get the averages in here. Also, I can have a really nice nested select statement here. So when we do all this together, this is when CTEs start to not run as fast as possible because the optimizer has a hard time figuring out a great plan for it. So in this case, you'll see that this will run for a few seconds. And the main point that I would say whenever you have to nest data like this, in fact, here you can see it took 18 seconds. We even have a total of 17 rows coming back. The nice thing to mention here is if you break this up, and you can either use table variables or temp tables, because we know we're going to have quite a bit of data here, I would recommend doing temp tables. This will allow the optimizer to break all the steps up and to optimize each individual step for you. So once again, all this code that we're going through will be attached to the link for the presentation so you guys can download this and play with it when you guys have some time. But this will just show you that we can break this down step by step here. So instead of having one big statement, which you would get with your CTEs that are nested, we also have everything broken down so we can know where we need to focus our tuning on, right? We want to spend time looking here because 100% cost of the whole batch is on this one statement here. So there's no value in focusing on what's down here, because if we want to make this even run faster, we could focus right here. So we already took it from 18 seconds to about 7 seconds by just breaking it from a CTE and breaking it into individual steps by leveraging temp tables. So with that, Scott, I will go ahead and turn it back to you, and then we'll have one last one, which we'll go over if we have time, depending on how many questions are lined up in the queue.
Excellent. Thank you very much, John and Em. I saw the whack-a-mole. I resemble that comment. I've done a few of that in my day, where you just start trying everything you can to get some performance out of it. So I've certainly started there, but I've graduated, if you will, to using software to get the job done. And one of the pieces of software that I like to use, and I encourage my customers and those I come in contact with, is to use a tool from Embarcadero, DB Optimizer. Though I spend most of my day when I'm working with customers in Rapid SQL and DB Artisan, working with administration and database development and helping them with queries and whatnot. I always tend to find my way over to DB Optimizer, and as such, it's my go-to tool for tuning for those specific examples that you pointed out. And I just want to show a few today. So for example, I've got a really, really nasty query right here. And in the past, I would totally take this query apart and look for performance gains at each section of it, all the way down to the nested query, then bring it myself. Once I've gotten that one tuned efficiently, then I'll bring it back up and try at the next level, and so on and so forth. But using DB Optimizer, I'm able to put it into the tuning wizard. And so in this case, I'm able to kick it off and let it run. So in this case, I only have a single query, albeit a complex query, but at the end of the day, it's just one statement. If I had multiple statements, I could easily set the tuning job to point at those and run. I could point it also to stored objects, to a stored procedure, and let it decompose the stored procedure into those statements that we can tune with DB Optimizer, and it'll walk through and tune each one of the statements. So again, looking at a poor performing stored procedure, right, we're able to bring that out, deconstruct it, and then potentially find the single statement that is the cause of the poor performance. So again, we're able to do that within DB Optimizer. Here, I'm looking at my different cases. So again, I'm looking here at my GIM database. It's just if I double click, I can see the statement again, same one that I just showed you before. Step through 9 tables of view. Here's my elapsed time, looking at some of the other, and you can see that I've improved it. 203 cases, right? This is just in a matter of probably 10 or 15 seconds for this specific case. It was able to generate 223 different iterations of this query. So now after I've executed this, I generated my cases, I've performed my detail analysis, which I'm going through and getting explain plan cost for each one, and then I'm going to execute, because at the end of the day, I want to see execution statistics for these. So again, I can look through here really quick and see where I get improvements. Immediately, anything in green is going to show me that I have improvements. So again, as I step through, right, I can see here's one. If I highlight this, it's a transitivity problem, right? So again, I know this query, I'm missing a join, and it's found it for me. So again, if I look at some of the other options, if I were to select this one as well as the original, I can compare these. So at any time then, I can look, what did DB Optimizer do for me? So in this case, we had this join. It added another join here for the broker ID, matching up. So again, I left off a join on purpose. DB Optimizer found it for me. If in this case I wanted to see what it was doing with my hash join query, I could select both of these as well. And sorry, I'm actually selected the wrong one, but here I'm actually comparing the explain plans. But let me hop back, and I just want to compare the selected statements in this case. So then I'm able to scroll down and see, here we had an order by, and here we specified the option hash join there. So again, DB Optimizer is able to go through and iterate through those. Now, as John mentioned, in some situations, it's indexing, right? Adding an index could help. In other situations, we may have too many indexes already there. Great thing about DB Optimizer, we can help you both ways. So in this case, I'm looking at, let me pull back the original query. There's the root query. So it's brought the statement back here. Left-hand side, the statement. Right-hand side is the visual SQL tuning diagram. Different than an explain plan, right? This is our way of deconstructing the query and then bringing it back in for you. If I select any of the nodes in the VST, we can look over here and see where it's referenced, as well as if there's any indexes. If I want to build something out, here's that sub-select. I can double-click there, and then we can see we have another in inside of that, and then a subquery there. So again, I can drill in as far as I need to expose this. And then if I'm looking over here at the exact statement, right, we can see where I'm referencing. So in this case, when I drill back out, I come to the bottom. Here's my index analysis. So as John mentioned, we have a potential here of speeding this up. But before I get there, let's scroll down to the bottom. So here, the index is defined on a column present, so it could be used. Right? So we can see all of the blue. What I don't see here, because I'm in a pretty clean environment right now, are indexes that exist that are not used, that will never be used by the optimizer for this statement. If I had those situations, those would be grayed out and listed. So I work with quite a few customers. I get to the point, and they have multiple indexes that are never used. So again, we can see that real easily with DB Optimizer. If it's green, telling me that the index is used by the optimizer when we run the statement. And then here are the ones that are in orange. If I select one, you'll see that DB Optimizer gives us the full description. Right? It's scanned via full table scan, but it has a filter. Right? It walks us all the way through why. So we could suggest implementing this index. If I go to the next one for client transactions, here it's scanned to full, but it has a filter. So maybe I just want to add this one. Just select, right-click, create indexes, and here's the DDL needed to create this specific index. So again, real quick, able to identify where I could potentially get improvements by adding an index and quickly add that. And just a real quick run-through of other things that we can see within DB Optimizer. I've selected the root. I can also go down and pick different ones. Right, if I wanted to look at the exist into rewrite, when I select that, now I'm going to recreate this. So again, we can see different ways that the VST is constructed. And again, in the bottom here, I have my index analysis. I can look at table stats. Right, we've got automatic statistics, and we can see these different settings, the number of rows that I have, and then the number of rows sampled. And then if I expand this, we can see the number of unfiltered rows. Here are any column stats and histograms that may be available, and then any plan guides. So again, at really quick, by dropping my query into a tuning wizard within DB Optimizer, I'm able to go through and taking into consideration behind the scenes DB Optimizer is working through some of those steps that John mentioned, and we're providing you with possibilities. So again, if you looked 203 cases, we can quickly narrow those down. Maybe I'm just interested in those with green, with improvements. I can go through there and actually find. Now again, you'll see some here in red. That's where my cases resulted in poor performance. So we want to list those as well, and you have control over how you'd like to configure DB Optimizer to do that. So again, it's just another method, biasly, I prefer to use when I'm working with queries on how to get those tuned and the most performant as possible. So on that, I'll turn it back over to John to take us home.
Thanks, Scott. Looks great. Do we have any questions out there from the audience from the demos that have gone over today or Scott's gone over today?
And so far, John, we're pretty clear. So obviously, they're getting a lot out of it with no questions.
All right. Well, in that case, we'll go over a bonus demo. So here's a real quick thing to look for that I also see repeated out there in the field over and over again. A lot of times we'll want to be able to determine if data exists in the table before we perform other actions. And out in the field, I tend to see this step here repeated over and over again, where we're going to go ahead and select to get the count from the sales order table, where we have some filters on it. And then if that count is greater than 0, we're going to do a whole bunch of stuff. In this case, we're just going to print records exist. But in reality, this is your decision tree to where your code really starts and goes on all kinds of fun adventures. So I'm going to go ahead and say, use our database here. We're going to turn on set statistics IO. And the reason why is because when this runs, I want you to see that we're scanning across the whole entire table here. So when that happens, we look at our execution plan, we see we're scanning. We're not able to stop once we know records exist.
Hey, John, this is Scott. I want to apologize. I didn't pass control back over to you. So if you could share your screen.
Oh, sorry.
Good. No worries. That was my fault. Thanks.
No worries. So is everyone able to see the screen? Okay, so as I was mentioning here, I see this repeated over and over in the field to where we're doing a select statement to figure out how many records exist here. So I have that count in there. And if we have records, so if there's 1 or 1,000,000, we're going to do a whole bunch of stuff. This is where your code really starts and goes on all kinds of fun adventures. For us, we're just going to print that records exist. Now, in SQL Server, you can use a terminating function called if exists. And so the big difference here is we're going to go ahead and stop here. So this is going to run, but once we have a single record in that if exists, we're going to go ahead and stop. So I'm going to go ahead and run the first part here. And we're going to see we're doing our scan, which you see there across the table. And the big thing to focus on here is we're doing scans across the whole entire table. So even though we only really care to see if we have 1 or more rows, we have to scan across every single row inside the table. When we actually go over here and look at our other option where we use if exists, this is going to terminate. So as soon as it finds a single record in here, it's going to stop and it's going to do your action that you need. So if you're in a scenario where you just want to check to see if something exists and move on based on it, I strongly recommend that you look at if exists instead of selecting the count of all that data, because here we're able to stop when we hit our first page after 3 logical reads. So a real nice tip for those scenarios where you need to check if data exists before you go down a fork in the road to do all kinds of other fun code strategies and SQL statements. And with that, Tamarian, I'll go ahead and turn it back over. And with that, we'll go ahead and go here to the last slide. So for everyone out there that would like to play with the sample code and go through the demos, you can download the code here. We'll also have a link to that video that will take you back over to Embarcadero's community website so you can watch that detailed video on how you can capture your workload so you're only focusing on the queries that really need the tuning help. And also my Twitter handler there is anyone can reach out to me on Twitter, or you can shoot me an email also if you have any questions over the demo codes. Oh, and it looks like we may have some questions. So can Tamarian or Scott, can one of you send or shoot a question?
John, I can do that, yeah. So one of them we had that just came up is, I think it dealt with your last demo. It was, does it matter if you select asterisk or select one? Select star or select one?
Ooh, good question. So the question was, does it matter if you do select asterisk or select one? And the answer to that is no. That changed a long time ago. In SQL, it may on another database platform. I mainly focus on SQL, so I can only give the answer there. But I would tell you to use if exist anyways inside of SQL so you can terminate as soon as you find that first row.
Excellent. And John, this is another question that came offline. A customer asked me to ask you, when you're out working with customers, as people start making the move to the cloud, to Azure, right, does that change your recommendations or your guidance to tuning queries?
It does, in fact. And to be very honest, I'm a huge fan of Azure and the cloud platforms, because you lose access to the underlying hardware. So it forces you to write really better queries that leverage the resources you have. So when I go to Azure, I really want to focus more on your baseline of what's currently out there and to be able to tune your top offenders to make them as optimizer friendly as possible. So I put more of a focus on code tuning because you don't have access to the underlying hardware and other things as you would if your database was on-prem.
Nice. I like that. I like that angle on how to put the importance back on that. That's a really good way of saying that. Yep. Excellent. Thank you. Let's see what else we may have. There was one here. Is there a performance difference between select count with one in parentheses and select count with star in parentheses or asterisk in parentheses?
The question was if there's select one and select star. And once again, with SQL Server, no.
Okay, well, actually this one, and I don't think there's any difference, but it was actually select count with a 1 in it or a select count with putting the star into parentheses. So I'm thinking the answer is still no difference.
Yeah, I mean, we can wrap up right here. I can even go right back here, and we'll just do both so that way you can see them side by side. But if I take this here, we'll just switch that to star, right, Scott?
That's it? Yeah.
Of course, we can't declare it twice. No difference. Same amount of reads, and you're going to see the same plan. Yeah, there really is no difference. In SQL Server going way back, there used to be, but that's on a non-supported edition. We'll just say that. But maybe 6.5 or 7 around there were some differences, but on supported issues, there's really no difference between the two.
Gotcha. All right, thanks. And that wrapped up the questions. Thanks, John.
Excellent. All right, well, once again, thank you everyone for attending. We hope you enjoyed the session and also the tools presented by Scott, which can help you with your tuning efforts. And we look forward to seeing you at a future webinar.